In this example, we're going to look at how to take implicit differentiation twice. It's going to require some substitutions in the end in order to get our answer in the most simplified way it can be. Okay, so the first thing we're going to do, since we're trying to get y double prime, is to just figure out what y prime is. Take the first derivative very simply, right? You just get 8x plus 2y y prime, right? Because we have to treat this, it's like the chain rule, right? But with implicit differentiation, you take the derivative with respect to y, and that's where you get 2y, and then times the derivative with respect to x, and that's where you get dy dx, which is just y prime. And then, of course, the derivative of 8 is 0. So that's our first step, right? Now we have to solve for y prime because we're trying to figure out what y prime actually equals. So very simply, you just move the 8x over, and then divide everything by 2y. Sorry, that should be 8x. To cancel those out, and you get y prime equals negative 4x over y. Okay, easy enough for the first one. But now, in order to find y double prime, right, taking the derivative of this, we're going to have to use the quotient rule. The top piece is our f, right? The bottom piece is our g. We're going to have to do the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So we better figure out what the derivatives of the top and the bottom are. Well, the derivative of the top is easy. The derivative of negative 4x is just negative 4, right? And then the derivative of the bottom is also very easy because the derivative of y is just y prime, dy dx. Okay, now all we have to do is plug everything in and then do some algebra. So derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. Clean it up. We've got the top plus 4xy prime, right? Because the minus cancel, make it a plus, all over y squared. But we notice we have a y prime here, and we can do a substitution with what y prime equals. So this is negative 4y plus 4x times negative 4x over y all over y squared, which now gives us negative 4y minus 16x squared over y, and then that whole thing is over y squared, right? All we did was combine this. Negative 4x times 4x gives you the negative 16x squared all over y. Well, now we have this complex fraction, right? A fraction inside of a fraction, and we have all these y's here, and maybe we can just clean it up, get rid of this complex fraction by multiplying the top of, the big fraction by y and the bottom of the big fraction by y. So you're basically just going to multiply by y over y and get negative 4y squared minus 16x squared all over y cubed, which is much nicer, right? That's much cleaner because we don't have complex fractions anymore. But then you're also looking at this and going, hey, wait a minute. I have a y squared piece here, and my ultimate job when taking derivatives, even when we're doing it implicitly, is to always list our answer in as much x as possible, right? You want to have your answer completely in all x's if you can. That's not always the case. Sometimes you have to have some y's in there. But you definitely don't want to have an answer with a y prime in it, right? That's why we did the substitution here to get rid of that, because you don't want to say the second derivative is defined by the first derivative. It's just too many levels. It's easier to just say it's defined as a function of x's and y's, which we've done now. We've defined it as a function of x's and y's. But if we can, it'd be nice to define it in just x's. So whenever you have a chance to sub out and simplify, you might want to go down that path and see what happens. And when you see a y squared here, you're thinking, well, I've got a y squared up here, and I can very easily solve that one and just say y squared equals 8 minus 4x squared, right, from here. And now I can substitute that in for my y squared. And now I have negative 4 times all of this stuff, 8 minus 4x squared, minus 16x squared. That's still all over y cubed. Now let's distribute it out and combine like terms, see what happens there. 8 times 4, right? Negative 32 plus 16x squared minus 16x squared all over y cubed. And lo and behold, that ends up canceling out those two terms, and we're left with just negative 32 over y cubed. That, right, is y double prime. That's our second derivative, and that's really the cleanest way we can reduce it. Now you might be thinking, hey, you just said we should try and list these things all in terms of x, and yes, we should, but listing it just in terms of y is just as good. I mean, ultimately we try and list it in terms of one variable, and it just so happens that we usually try to make that one variable x, but in this case we have it listed in terms of one variable, that variable being y, and that's perfectly fine. So this would be the best way to list y double prime.